Hi everyone, welcome to this video. My name is Rutvik Shankar, and in this video I'm going to explain to you about a simulation of a sleep state controlled HVAC system. So what is a sleep state controlled HVAC system? A sleep state controlled HVAC system is a HVAC system where the HVAC system alters the ambient temperature based on the physical state of a person. In this particular case, this simulation, the HVAC system changes the ambient temperature based on the sleep state of the user. Okay, this project has been implemented and simulated on LabVIEW, and this before you is the dashboard of the simulation. Let's go into the dashboard and see all the components and their functions. First, this is the on-off switch. This is a Boolean on-off switch, and it's as simple as they come. The main function, the only function rather, of this switch is to turn the system on and off. So on, off. Okay. On the top right corner, you see the sleep state indicator. This is a light which indicates whether the system is in sleep state or not. So when the light is on, it indicates that this system is in sleep state, and when it's off, that it is not in sleep state. Here is the heart rate or the heartbeat display unit, waveform display unit. So this displays the heartbeat of the user. This is the AC temperature display. This is a graphical representation of the temperature. This is not only a display, but it also can be used to control the system. Okay. Here are a few displays. There are two displays, digital displays here, and two input units, two functional displays, and there is one mean heart rate display. Let's look into them. This is the instantaneous heart rate display. This window shows the instantaneous heart rate of a person. And this is the resting heart rate display. So what is this resting heart rate display? It displays the resting heart rate of a person. How do we obtain this resting heart rate? Resting heart rate is the heart rate at which the person, heart rate when the person is not doing any physical activity. For example, sitting on a chair and sipping coffee, or sitting and watching TV, or as opposed to exercising or playing football or sleeping. So when a person is exercising or playing football, the heart rate increases. Okay, this is called the physical activity or a strenuous heart rate. And then when the person is sleeping, the heart rate reduces, and this is called a sleeping state heart rate. Okay, we'll see how we get all these values. And there are two input units here, input windows here as well. First is the input heart rate. Since this is a simulation, to display the working of the unit at our ease, we input the heart rate ourselves. Okay, the instantaneous heart rate is input by us itself, the user, for display purposes. But in the actual physical project, this instantaneous heart rate will be provided by either a smart band or a smart watch, or similar things devices like that. Next, the temperature adjuster. So this is equivalent to your thermostat that you have at that is present in most households. So here you can enter the temperature and you can see the temperature display change. So this is about the dashboard of the sleep state controlled HVAC system. Now that we know about the dashboard of the HVAC system, let's look into the internal circuitry. Okay, this is the internal circuitry of the HVAC system, and essentially this is where all the magic happens, if you may. So this internal circuitry can be divided into three broad areas. This is the instantaneous heart rate generator. This is the mean or the resting heart rate calculator, not the mean, I'm sorry. This is the resting heart rate calculator, and this is the logic unit. So let's go into each of these units and see what each block does, and their inputs, outputs, and their function basically. So this is the input heart rate. As we saw in the dashboard, we enter a heart rate here. Okay, so this block, what it does is, it is an interface between the dashboard and the internal circuitry. So whatever value you enter in this window here is taken from the dashboard and supplied to the internal circuitry through this block. And this block outputs the value that you have entered in the integer format. Next is the square wave generator. So what happens is, even in smart band or a smartwatch, what happens is the smartwatch recognizes only one of the peaks. Okay, it when you see a CPR and all, it has all these peaks and crests and all that, but a smartwatch does not output that. It outputs a square wave itself. So a square wave is when the pulse is when the pulse hits, it generates a crest, and when in all other situations it generates a low. So this simulates that, and the input that we are giving through the input heart rate is taken as the frequency for this unit, and the square wave is generated, and the output of this is fed to the heart rate waveform display unit and the peak detector. Okay, the heart rate waveform display unit, this acts as the interface between this and the heart rate waveform display unit here. So whatever is the waveform that is there is displayed on the dashboard here. Next, the peak detector. So what this peak detector does is it takes the square wave and it calculates the number, the sum total of the peaks and the lows, both the peaks and the lows. Then this value, which is an integer here. So this peak detector basically converts this waveform into an integer value, is inputted into the arithmetic units. So what do these arithmetic units do? Since it is the sum total of both the peaks and the lows, we do not need it. It is not the exact heart rate. What we need is the exact heart rate, and that is obtained by dividing this value by 2. We need only the peaks, so we divide this value by 2. So this is a divider, and this is divided by 2, as you see here. And there is a slight problem that happens when the heart rate is odd, and hence we add 1 to this unit, so to get the desired heart rate. Okay, and this is output. This integer value is output is taken by the one by the logic unit, and the other by the instantaneous heart rate display, as seen in the dashboard here. So this is the value of the instantaneous heart rate display here. Okay, now let's go into the resting heart rate calculator. This whole block which you see here is the resting heart rate calculator. What does this resting heart rate calculator do? So resting heart rate, as I told you earlier, is the heart rate of a person when he or she is not doing any physical activity. So how do we get this? Medically, we know that the statistics observed over 24 hours time period, and the over 24 hours time period, the most common heart rate is the resting heart rate, because most of the time during the day a person is sitting, and working at a desk or something like that, except for sports people, which is a different category altogether, and the resting heart rates are also high. So to get the resting heart rate, what we did was we obtained the data of a person's heart rate for 24 hours. Okay, this data is recorded every 3 minutes over the time period of 24 hours, and this data is fed into a spreadsheet. In this case, we have used Microsoft Office Excel to store the data, and that data is fed here. Okay, this function read spreadsheet. What it does is it takes the data from the spreadsheet, that is Microsoft Excel, and it takes it into the LabVIEW platform. Next, this is the matrix operator. What it does is the spreadsheet that we have obtained is an n cross n, is in the form of n cross n. What this read spreadsheet does is it converts this spreadsheet into a matrix of n cross n. But we don't need so many values, right? We don't need n cross n. So what this block does here is it converts it into 1000 cross 1 matrix. Okay, because all the data in our Excel sheet is limited to the first column itself. Okay, all the data is limited to the first column, due to which all the unnecessary blocks of the Excel sheet is removed. Okay, so this converts this n cross n matrix into a 1000 cross 1 matrix. Next is the matrix operation 2. For this mode calculator, this is what calculates the resting heart rate. We need a row matrix, not a column matrix. Here, the output of this unit is a column matrix. So to convert it into a row matrix, what we do is we transpose it. Okay, the function of this block is to transpose it. So from a 1000 cross 1 matrix, it is converted into a 1 cross 1000 matrix. Okay, so after this, this data is fed to the mode calculator and the mean calculator. The mode calculator. What is the mode of the data? The mode of the data is the most frequent observation in that data. As I told you earlier, the resting heart rate of a person is his or her most frequent heart rate. Okay, and then the mean calculator is the arithmetic mean or the average of the whole data. This value has very little or no significance in our project, but still we have calculated it for user experience. So this mode of this data is fed into the resting heart rate display. So this resting heart rate display that is here is from here. Okay, from here, resting heart rate display, and this mean heart rate display is this mean heart rate display. The other output of this is, see, the output here is still in an array format. We need to convert this array into an integer format. This because the logic block is designed in such a way that it takes only integers, because even the instantaneous heart rate is in integer format. The heartbeat also should be in integer format to have a comparison between the two. So this block here converts this array into an integer. Okay, and this is fed here. Now let's go into the logic block of the simulation. So this is the logic block of the simulation. This is the program that this is the code that takes the logical decision. Let's look at the inputs of this logic block. The inputs of this logic block are limited to this side and this side. So first input is the instant heart rate that is supplied from this instant heart rate generator. The second one is the temperature adjuster. Okay, so this temperature adjuster, as we saw here in the dashboard, is this temperature. So let's say people maintain their house temperature at 20 degrees Celsius. Okay, so that is the temperature that is inputted here. Okay, and then the resting heart rate, of course, this is the benchmark. So the first line of the code and the output is the AC temp out. So this is the temperature at which the system controls the HVAC system. Okay, that this simulation controls the HVAC system. If this heart rate if the AC temperature is the same as the input temperature, then we feed it in the same way. If the system is in sleep state, then we feed another value, which we'll see later. And this is the sleep mode indicator. This is a flag sort of a thing, where if the system is in sleep mode, this light, that is this light on the dashboard, turns on. Okay, let's see the code. AC temp out is equal to AC temp. So first we initialize that AC temp, that is this output temperature, is the same as the AC temp in, or AC temp, that is the input temperature. So the first line, the output temperature is same as the input temperature. In initialize sleep mode is equal to 0. So if the system is not in sleep mode, then this flag will be 0 and this light won't turn on. Okay, now this is the logic. Here. If instantaneous heart rate is less than 0.8 into heartbeat, that is, if the instantaneous heart rate, that is the value here, is less than 80% of the of the resting heart rate. Okay, as I told you earlier, a person is said to be in sleep state if his or her heart rate is 80% or less than his resting heart rate, his or her resting heart rate. Okay, this is a medically this is how it is established medically whether a person is in sleep state or not. Okay, so let's say a person's heart rate, resting heart rate, is 100 beats per minute. Okay, it is a random value that I'm taking. So let's say a person's heart rate is 100 beats per minute. Okay, resting heart rate. If the person's instantaneous heart rate is less than 80, okay, 80 beats per minute, that is 80% of 100, then the person is said to be in sleep mode. Okay, so there are various phases of sleep, and in the most relaxing part of the sleep, a person is said to have 80% of the resting heart rate. Okay, that is what we have inputted here as the logic. Okay, so let's look at it again. If the instantaneous heart rate is less than 80% of the heartbeat, this heartbeat here is the resting heart rate. So if the instantaneous heart rate is less than 80% of the resting heart rate, then AC temp out is equal to AC temp plus 3. So what we are doing here is, if the person, through this line, we are establishing whether a person is in sleep state or not. If the person is in sleep state, this whole if statement becomes true, and we go in here, and AC temp out is equal to AC temp plus 3. We increase the temperature. We increase the ambient temperature by 3 degrees Celsius. Okay. And along with that, we say sleep mode is equal to 1. Sleep mode is for the sleep state indicator. We say it is 1. So this light goes on. Okay. So that is the logic unit here. And there are a few auxiliary components or blocks also. First is this timer block, which is at 20 seconds. And second is this on and off switch. So first we'll look at the on and off switch. This basically is the same. This is connected to this switch on the dashboard, which turns on and turns off the system. This 20 seconds here is this whole, you see this gray color rectangle here. This whole block is activated every 20 seconds. Why is this? This is so that, when the person is just falling asleep, when the heart rate is varying at 80%, it's not exactly fallen below 80%, it is falling below 80% and it's increasing from 80%. Let's say it's at 80, then it's at 79, then it's at 80 again, then it's at 81. So to prevent the flickering of the to prevent erratic change in temperature, erratic change in the HVAC system's temperature, we have activated it every 20 seconds, so that when a person is falling asleep, after he completely falls asleep, or when that stable sleep state is reached, then the system switches to sleep state. Okay, so that's about this. This whole system, as I told you, is this whole loop executes every 20 seconds. This is a while loop. Okay, executes 20 seconds. So this is about the logic unit. This is about the internal circuitry, sorry. Now that we have seen the dashboard and the internal circuitry in detail, let's see the system or the simulation working. This is the input heart rate. This is the heart rate where we are, this is the heart rate which we will be simulating. So we can observe that once this heart rate falls below 80% of the resting heart rate, there is a spike in temperature by 3 degrees. Okay, this is the temperature adjuster. This is where this is equivalent of the thermostat at common households. This is the temperature at which the HVAC system would exist if it was not controlled by this project. This is the temperature indicator, where you can see that if the system is in sleep state, then there is a jump of 3 degrees Celsius. Let's look at this in action. I have stored all this data in Excel sheet. I'm choosing the Excel sheet here, and voila. So since the heart rate is more than the resting heart rate, the system is not in sleep state as indicated here. Now let's change the system to less than the resting 80% of the resting heart rate. See, as soon as the system recognizes that the input heart rate is less than 80% of the resting heart rate, the sleep state comes on and there is a spike in temperature. If you see this thermometer, it is reading 23, but whereas the temperature adjuster is showing 20. Now let's say the person wakes up again, the heart rate is back to 85. And the sleep state is gone. Okay, this is essentially the working of the simulation. Thank you for watching.